Okay, well, welcome to the talk for Houston Perl Mongers. What are we? Is it January 14th, 2020? So I'm going to be talking about atomic operations in Unix and through Unix, some things that we can do in Perl to access these atomic things. Um, as with most talks, when I propose them, I'm not an expert, and it's more pressure on me for myself to look a little more into it. And this was no different. And I ended up finding some pretty interesting things and cutting out some things that I really wish I could have gone more into. But in any case, we'll proceed. Let me know if you have questions or if you see mistakes, because I'm sure there's certainly some mistakes here. But I do have running code, and sort of like the one on forking, I've got some examples. Okay, so what are atomic operations? Atomic operations are things that happen or they don't happen at all. So most people, although this is not a talk about databases whatsoever, there is a concept of atomic operations in databases that we're probably more familiar with than anything, called transactions, where you can start doing things to the data or the database, and then in order to make them permanent, you can commit them, or if something goes awry, you can roll them back to the state of the database, where, from right before you began the transaction. So what we're talking about here on Unix is our atomic things that we can do through the kernel, and oftentimes utilizing the actual hardware to ensure that things, fundamental things that operating systems do, are not done simultaneously, because if they are done simultaneously by different processes, then that can really screw a lot of things up. And that concept is so important in operating systems that you get hardware support for these atomic operations. And at the very least, you get software support. So they're primitive operations, and we can actually use them as synchronization barriers, or we can utilize them in our programs for maybe things they weren't intended to, but it still gives us the atomic assurances that they provide for the operating system. Now, I think I can write on here. So this URL right here is the inspiration for this talk. I guess based on the URL, it was created in 2010 at this guy's blog. I found it sometime after that, and I thought it was so cool that I've always wanted to do a talk about this, but I'm not going to do it much justice. I highly encourage you guys to go take a look at that, and then there's some links there also on that page that can bring you to some other information. All right, a couple of notes about this talk. Like I said before, there's a lot in this topic to cover. I ended up just really talking about atomic operations that can happen within the file system itself. So there's atomic memory operations that you can utilize. There's special hardware that you can use for accessing other type of primitives. We're talking just about file systems. The one benefit to that is that we're really just going to be talking about command Unix utilities and Perl functions that we all have everyday access to. One other thing I would like to note is that most of this stuff is platform dependent. It depends highly on the kernel implementation. It depends highly on the file system implementation, whatever file system you may be using. So a lot of the assumptions that something is atomic is based on, does the kernel implement it? Does the file system implement it? And in some cases, that even depends on the hardware itself, whether the software even has access to do atomic things. One good thing to read, especially when we're talking about the Perl side of it, is Perl port. If you just do a Perl doc Perl port on your command line, or you just go to this URL here at perl.org, then you'll see it's got a wealth of information about the different functions that tend to rely on system implementations. It's very interesting to begin with, just to see how Perl deals with different architectures and operating systems. But in a lot of these cases, the atomicity of the commands really does depend on the operating system itself. And it's no surprise that a lot of the problems, a lot of the warnings that you see are either related to Mac OS or Windows. And surprisingly, I've seen, at least anecdotally, there are more warnings about Mac OS not being atomic for one reason or another than Windows. And it's probably because how they have bastardized Unix. But in any case, that's kind of like a caveat. Let me move on. Okay. So the motivation here is that
I could briefly address that, especially
sure.
this comment is from a decade ago.
What's that?
I could address this, especially if that feeling was from a decade ago. There was a time, for example, on the Mac OS, it related to disk syncing. So usually there was a Unix command that you could call that, or it returned once it guaranteed the data was saved to disk. But Apple, in their wisdom, decided to change the behavior of something with defined behavior, that it just returned immediately, even if it had not been saved to disk. And the reason was for performance. And then afterwards, people had to start using a different command to check, yes, it really, really was saved. That might be related to what you're talking about.
Probably so. Thanks for adding that. So as far as the motivation goes, having atomic operations for doing things is useful, especially if you have multiple processes that you're spawning. And this is kind of as a throwback to my other talk about forking. If you have multiple child processes that you are forking, and you want to do something other than just fire them off and then let them finish and die, then you can use these atomic operations to more or less coordinate the child processes. You can also ensure safety and operate over the same, say, files from multiple child processes without having to really embed a whole lot of that protection within the program logic itself. So that's where we get in here. This is from the web page. I've got some screen caps of some things they say, because really I couldn't say it any better. But we can use them as building blocks for thread safe and multi-process safe programs without mutexes or read-write locks. And I'm sure we have all gone through and done our own blocking at a relatively high level in our Perl code. When in fact, if we were aware of these, maybe we wouldn't have gone through the process of doing it. And ultimately, anything we would have done or have done is not going to be any more efficient than what we can do through the operating system, through the kernel. So here, and I think this quantifies it pretty well. It's stupid to spend CPU time locking around an operation that's already atomic. So I know that one of the big epiphanies that I had when I read this blog entry was that I was doing a lot of things unnecessarily. I didn't realize that some simple commands at the command line or through Perl were atomic. And I was certainly familiar with the concept of atomicity and threads and multiprocessing, but I was not really that well aware of some really accessible things that we can use to guarantee those protections. So this is my alternate title slide. I think some of y'all can appreciate that, but it drives home the point that there's a lot of things that the operating system can do and that the kernel can do that we shouldn't spend CPU time. We shouldn't spend programmer time. We shouldn't spend mental cycles trying to develop the logic and reasoning about the correctness. Okay, so I'm not going to be talking about a ton of different commands or a ton of different Perl functions, but these will give you a taste of what's out there. This is not an exhaustive list, as it was mentioned before in that blog cap, but this gives you a good idea of what's potentially out there. I also wanted to mention I don't talk really in depth about the system calls. There are other system calls that are atomic. There are GCC provides an atomic library that gives you some pretty refined access to what either the kernel is able to do, or maybe even the hardware system is able to do in terms of providing atomic operations. But what we're going to talk about today, or this evening, we're going to talk about the move command. Okay, MV. MV is just moving a file here. MV minus T, and that's actually what I have the example of. That tells the move command to atomically take an old symlink and switch it to a new symlink. So whatever the target of an old symlink is, it will move it to a new. It will move that target to a new symlink, but it will do so atomically. Make mkdir, make dir. That is an atomic command. I didn't even realize that until I started working on this presentation, and it actually turned out to be the most accessible thing to use. Um, so obviously, it creates a directory. The error code that you get if the directory already exists is e exists. And this is true both through the command, the command line command, and the Perl command, make dir. So the Perl actually, and I'll show this, I think in the next slide, Perl actually calls the same things that this command does. And that was another nice thing to see, is that in general, for the system level stuff, Perl is using the same system calls as the command line utilities. And on one hand, that's what I would expect. But on the other hand, it was nice to see that, because I never really thought to even look into that. Let's see. So it ultimately ends up using the same mechanism as open. And I'll show that's the system call that sysopen uses in Perl. And I'll show you what this OEXCL is. And then this last point is anything that uses so we're going to be talking about the move command, the make dir command, and then the sysopen command in Perl. So the open sys call, you can open it in modes, and I got a Perl example coming up, but the mode that you are going to be opening it in is whatever you're going to be opening, you're telling the kernel basically you want to create the file, and that if the file exists, you want to throw an error. And this is I guess it's ORing those two values together. But that's how you pass it in. Now, what do I have here? Okay, I already talked about a lot of implementations are non-portable. We don't really run into that issue a whole lot when it comes to Linux. In my examples, we're all run on Linux, and I've got a terminal window open up to Linux. It's CentOS 7. But they do rely on the system kernel capabilities, and in a lot of cases, especially on your more expensive and exotic hardware, there's some pretty interesting atomic capabilities for the hardware itself. And then, since we're talking about just file systems, I thought I would mention this. They generally don't work, at least for the move, and I don't have this a demonstration for this, but it seems you can probably convince yourself that this is true, that there's no guarantees of atomicity if you're using the move command across either file system barriers or a local versus network situation. And a good example, this doesn't really apply to going across the file system boundaries, but the reasoning for it not working when you're dealing with a local and um, a network type mount is that you're dealing with two different kernels, and a kernel is not going to be able to guarantee atomicity with another kernel unless some kind of special setup is already happening. Okay, moving along.
Incidentally, you said you weren't going to talk about databases, but I will mention that they have a mechanism for this. It's called something like two-phase commit, which allows separate machines to synchronize as well.
I think I've heard of that. Good deal. Thank you. Somebody's dog's barking. It's not bothering me, but I don't know if people can hear me over it.
I can hear you.
Cool. All right. So why are these things useful? It can provide some system level guarantees against race conditions, and that's really what we're after. It can remove the need of the parent to process logic to deal with these race conditions. And then it simplifies the programming part, the logic part, because the programmer doesn't have to include the locking logic within what they're doing. And that allows you to really focus more on what you're doing, and at least within the sphere of Perl, you're programming do what I mean more than do what I mean here, make sure that these files don't overwrite each other, make sure that these processes don't clobber whatever the other one's doing, blah, blah, blah. So it being able to abstract these out and just almost forget about the need for locking is nice. Okay, so what I want to show here, so this is just a screen cap from that blog entry where he talks a little bit about the make dir command, and it just talks about if the directory already exists, it throws this exists error, and what I show here is just exactly that. So I should have like put boxes and stuff around here. But in any case, what I show here is that this is CentOS 7.9, and then Perl 5.14. Yeah, this is an old version of Perl, but and then what else do I show here? So what I'm doing here, I'm actually using strace to show the system commands and any errors that might come. Now this is the initial make dir, and the directory is foo, and I'm just showing the last 7 lines of the strace here. But in any case, it shows that the let me see. It shows that the right here, I believe that the exit code is that it was succeeded. Does that show it succeeded? Well, it's supposed to show that the directory is being created, because the next one I'm trying to create the directories while they already exist. So let's say that it was created okay there, and then the next call right here, that's calling make dir from the command line, and we're showing an strace that foo already exists. Okay, and since it already exists, this is the system call here. It's throwing this exist error because it's telling us that the file exists. Sorry, I'm not like the best at reading strace, but I was able to show also that within Perl, you can see I'm running Perl and then make dir foo, and that's the Perl interface to the make dir functionality. It also is throwing this exists, as one would expect. So all I wanted to show there is that the make dir, that the utility that you're calling in the command line, and the function that you're calling in Perl is doing the same thing. Okay, now what I'm showing here, this is a little more complicated. This is a bash script example of how make dir is atomic in the face of a bunch of child processes. So all I'm doing here, and I don't know, a lot of you were here for the fork talk where I showed bash scripts forking and Perl scripts forking. All I'm doing here is I'm spawning 10 child processes, And I did want to point out something here. And I don't know if I should correct the slides from the previous talk or have an addendum or something, but I realized that when I was trying to determine the process ID of the shell that I was in, the interactive shell, and then the script I was running, which is the parent process, and then having the child become aware of what its own process ID was, I was doing things wrong in the some of the examples in my previous talk. So what I wanted to point out here is that the shell PID, so I'm running this as a script in an interactive shell. PPID, this thing here, is something that is available within, at least within Bash, that contains the parent ID of the shell. Okay. The script that is running is the double $sign. And this is the script that you run from the command line. And we're all familiar with that. So PPID is the interactive shell's process ID. Like if you do PS and you see bash or whatever. The script is double $sign. And then the child, since we're using a subshell here, you see the open and close parens. The child, this is the body of the child here. This whole from this opening parens to this closing parens, everything in there is being executed by the child. And then this ampersand is saying background, this subshell. Well, since we're using a subshell, we can use this bash PID variable, and that within the child will tell the child what the process ID of the subshell is that the child is, because the subshell is the child. It's just running the commands in that. So in any case, I wanted to point those things out because that was something that I had to work out. But effectively what we're doing is there's a child, the child process is generated, is what happens between these parens. All of this happens per child, okay? This sleep command here, this really long thing, what I'm doing there is generating a random sleep to sleep less than a second, because I wanted the processes basically to not execute or not finish in order. And all I'm doing here for each child process is making each child sleep some random amount of time. And then they are all calling this make dir and then this $source, which is this lock dir here. So all the child processes are trying to create the same directory name. And then I'm just redirecting the error to dev null because I really don't care about it. But the stuff that within the child that is relying on the atomicity of the command it's between these two comments. It's this make dir here. Okay. So out of the 10 children that get spawned, child processes that get spawned, only one of them will be able to actually create the directory. Okay. So, but all of them try. They don't check to see if the directory is already created. There's no lock file to check first. They literally just all try and create the directory. And then we can tell whether or not it's successful by just checking the exit status, the $? So if the command was successful, and this will happen for only one child, then it will be equal to 0. Otherwise, we're going to say it failed. All right. And then over here on the right-hand side, all this stuff, that's the output of running this script. And you'll see that obviously the first line here is, well, in this case, it was the fourth child with this PID, 30630 won the race. All the other 9 children failed to create it because it was already created. So that's an example. This is probably the most basic example of just saying, hey, children, go do this. and I don't care who does it first, but it needs to get done. And what this demonstrates is that make dir can be used can be used safely without having every child generate or check for the directory first, and also that you can detect when it's failed and then handle it somehow. You could do a retry. You could literally, in this case, you could have a generate some kind of for loop that has each child, basically do something if it was able to make a directory, and then when it is finished with that directory, it deletes that directory. And then say you've got a pool of children who are just spinning there waiting to be able to get their chance to create a directory. You can use that. You can use that to coordinate some barrier for your child processes to get through before they proceed. Now, making the directory may be part of what they need to do, but it can also just be like a lock file. And so this is a really good example of the essence of what this gives you, or what the atomic commands give you. This is an example using Perl. It does exactly the same thing. In fact, the output is exactly the same. I'm forking it the Perl way, and I've got a random sleep here. It just looks, it's just in Perl. There's really not much different except how I detect failure, and that's right here. I've got the make dir in an eval, and here I'm just checking to see whether or not return is defined, or if it's a truthy value. If make dir succeeds, I get a 1. If it doesn't, it'll die, and then return will be undefined. So as you can see with the output, and I can run these scripts here shortly, but it does the same thing. So we can see that it runs fine in Perl. This is the I guess the wait for the parent child to make sure all the child processes are finished. We covered that in the last talk. And then here's some cleanup, and then print done. And then this is I just use time high res sleep, and then some small value for the sleep bound. All right. All right. So MV move -T, what this does is it deals with symlinks. So we're going to be using something that we're basically going to be redirecting an existing symlink to a new symlink. And we will show that this will also fail if the new symlink already exists. And we basically can use it in the same way that we were using that make dir, the atomic property of make dir. One thing to point out is the I guess the higher level, I don't know, the system call that move any atomic operations in the move command rely on is rename. Rename is also used a lot in the Perl methods that are used, but it is rename is atomic, and that's really where a lot of the atomicity comes from. Is this rename syscall? In fact, in Perl, there's no move. In core, it's called rename. That's because that's closer to the system call. That's what's actually happening when you call the MV command at the command line. So here, what I've got here, this is set up a little bit differently, but I'm using MV-T to provide some guarantees that things are happening atomically, even though all the child processes do complete the thing. They are happening. They are happening completely each time, even though all the children are trying to do it at the same time. And rather than the first child to get to do something being the winner, I'm not declaring this process the winner, but I'm saying that we're determining the very last process or child that got to do the thing here, if that makes sense. So what I'm reporting in the output is the last PID to do something was whatever. In this case is 10071. And that thing is, let's go through the code. So first thing that each child does, and again, this is like that original, the bash example for make dir, except I'm running, spawning 100 children. There's no sleep statement in here at all. Okay, so the all 100 children get spawned very quickly, and they're hammering the kernel to do this. I'll do the same thing at the same time. But each child process creates its own directory with its own process ID name. So it's going to be my dir dot whatever the process ID is. That's what I got. This bash pid up here is a child's process ID. And then each child is going to echo a text file into the directory it just created called info.txt. And all it's doing is echoing its own process ID. All right. So each child creates its own directory. No problem there. And then within that directory, it creates an info.txt with its own process ID. All right. Good deal. So then what we do, each child creates its own specific symlink here. Okay. So I'm creating a symlink called symlink.processID or child that targets this mydir.child. Okay. Now here comes the atomic part. Again, all the children are doing the same thing. This mv-t is changing the target of the first symlink that each child has created, which it created safely because it was using its process ID, to one that is called iwin.yup. But all of them are trying to retarget their symlink, which is differently named or unique, to this symlink that is the same for every process. Okay. So what I'm trying to show here is that each process will do this and it will complete, but at the very end, only one will, it will only be pointing to whatever the last one was that actually got to complete this operation. And then here, we'll see. Now this is checking to make sure that there were no failures. Essentially making sure that all the child processes were able to do it completely, because that is what is supposed to happen. We're supposed to see that each child process is able to switch its symlink from its own unique symlink to the main or the global or non-unique symlink and have it complete successfully. And what this shows is that the operating system but by guaranteeing its atomicity, it is essentially serializing all of these concurrent processes. So it's making the overall effect is all these 100 processes are running. Maybe not all 100 are running at the same time, but a bunch of them are running at the same time. They're all trying to switch this symlink, but the operating system, because the underlying syscall for this mv-t is atomic, it has the ability to effectively force or serialize all the processes to wait in line. And how it does that, not my problem. I mean, I'm sure it's a really cool and very intricate process, probably uses something in the hardware, but that's I guess the whole point of this is I don't have to worry about that. I can just assume that even if you've got 100 child processes hammering this one command where it wants to target its own symlink to a symlink, the same symlink that all the other child processes are trying to use, I know that that operation will get a chance to complete, and it will complete fully, and it will complete successfully. And that's the guarantee that the atomic operation is giving us. So we don't and that's the beauty of this. We don't have to worry about how it's implemented. And then, so finally, as I said, all the child processes get a chance to do this. So at some point, it would happen very quickly, but at some point, all of the symlinks that were the unique symlink.child process ID, whatever, are all going to be targeted in turn at some point to this single one i-win.yup. And then at the very end, it will be pointing at whichever process got to do it last. And then what we've got here at the end to show that is I'm extracting the last PID from the whatever directory this symlink iwin.yup is pointing to. And then that's the output that you see here. So you can see that these processes, the output is happening. And another thing I wanted to point out, which also makes me pretty sure that this is actually serializing the processes, is that I didn't get any, even though I was doing 100 processes, I didn't get any, partial output where the standard out of one process stepped on the, was shown in the screen in the middle of the standard output of another process. They all happened, they all got printed out nice and sequentially. It happened quickly, but they all got their own line. And then, so this very last success here, child 97 with PID ID 10071, that is from the for loop. Okay, that is the very last child process that was able to touch the symlink and redirect it, and then hit this block where it checked to see if the command was successful or not. And then the next line after that is outside of the for loop, and it's dumping the PID from whatever the last process ID that was able to retarget that symlink, and it is the same child process. And I ran this a bunch of times, and it was always, although the ordering changed, this always worked. So that pretty much convinced me that things were working fine. So that's what the MV-T gives you. It allows you to atomically retarget one symlink, or the target of one symlink, to another symlink. And you can see this isn't a race. It's not first child process that reaches it wins. It's just for purposes of showing here, it's the last process that touched it is where it's pointing, A. And the other point is that all of the child processes that tried to execute this atomic command were able to do it so successfully. All right. This does the same exact thing in Perl, except Perl doesn't have a move command in core. It uses rename, which, as I mentioned before, is the system call that is used underneath move, the move utility. It does the same thing, so I'm not going to go through it as meticulously, but is there anything I wanted to show here? Yeah, I'll show the this is the atomic rename. Okay. And so in Perl, when I run this, it does the same thing. It behaved the same way. Each child process is creating its own unique symlink, and then that would be up here. It's doing a make dir symlink. This is where it prints the child process to the info.text, and then it does the rename. And then at the outside, so that happens within a child body within the for loop. And again, it does it for 100, spawns 100 children. And then outside the loop, we got the wait here. And then here I am reading the contents of that last PID, and it prints out last PID. And again, it's the same exact results, which was good to see. So this is from the for loop, this last line, success child 89. PID 1187.0, and then this last line is outside the PID when we're actually dumping the contents of the last symlink. So yeah. Okay. So there wasn't. So as far as command line goes, the mv-t and the make dir were, I guess, the most accessible commands that I could find. I probably could find some others if I had allowed myself some more time, which I did not. But for Perl, there's this sysopen. Okay, now the reason I found, and this is not contained in that blog entry. What ended up happening was within the blog entry, I saw it mentions the open syscall, where if you open it in a certain mode, then it would provide some atomic guarantees to the creation of the file, and it would cause the syscall to fail if that file already existed, which is not that is not something that within Perl, like Perl Open, will give you. But what you can do, or what Perl does have, is this this call sysopen that I found, and that is just I guess a more raw access, or it's more raw access to the calling semantics of the open syscall itself. Now, what I'm doing here is basically I'm doing the same thing I was doing in the make dir example, where the first child to create the file wins. So I'm not going to go and have to explain that too much, but what I did want to show is the sysopen call. Okay, so this is the sysopen call. It's done in an eval block. And then the semantics are very similar to the open call in Perl. There's the file handle, and here it takes a lexically scoped scalar. So this is the name of the file we want to open, and then here is the mode. And I believe well, yeah, definitely in the open command, the open function, the ordering is a little different. So if you were to go, and I can show you, I use open here. Here we go. Right here. This is the file handle. This is the mode, where the second parameter is the mode, and then it's the file that you want to open. I didn't really look too deeply into if I can recreate this effect within the open function using one of these open mode, these mode shorthands. I didn't think I could, but I'm actually a little curious, so I'll take a look at that later. I don't think I can, though, because what this provides, sysopen here provides you, is a way to basically compose very precisely the kind of mode that you want to pass to the open syscall. And in this case, if you want to set it up so that the first child process that creates the file definitely creates the file, and then if the file does exist when other child processes want to create it, then you would or together these two constants, o create, obviously create, and then o excl, which is exclusive. So what you're doing by combining these two is telling the open syscall that you want to create an exclusive, or exclusively create a file, and if another process tries to create a file using this mode, that will instantaneously fail for that process. And the underlying bits of the open syscall implementation that actually create the file and ensure that it's exclusive is atomic. So this can be used like I've been showing in other examples, for the purposes of the first process that creates it will win. All you need to do is detect if the syscall failed or not within the child. So let's see. Okay. we're getting close to the end. There were surprisingly few Perl modules that I found that actually took advantage of this these concepts. There were a lot of other modules that do efficient locking, and I didn't get into like the F-lock stuff. And there's, like I said, there's a whole range of syscalls that you can use that do provide some low-level locking primitives and other cool things, either with a file system or with memory. But I was looking for I was pretty much looking for something that had pretty easy access in the command line as well, and that's how I settled upon the MV-T and then the MakeDir. Close the door, please. Okay, sorry, I'm being invaded. Okay, so one of these modules is file symlink atomic, and with this, hold 1 second, please. All right, can y'all hear me? I hope my mute was working. Okay.
Yeah, go
Yes,
ahead.
probably
Okay.
didn't want that
So what this
conversation.
claims to do, or what this does do, I don't have any reason to think it doesn't work, is it doesn't replace the symlink call, the atomicity of the Perl symlink call, but it does provide basically what I was showing with the MV-T, and you'll see here in your shell. This is basically what the author of this is showing, that this is what you would do in your shell, and you'll see that. Let's see. There we go. There's the MV-T. Um, all right, 1 second. Okay. Sorry about that. Speaking of child processes. Um, okay. Anyway, so what this does is provides basically the a Perl equivalent of the MV-T, and where you want to create where it creates a symlink, it creates a symlink, and then you can redirect that symlink to a new symlink atomically. So this is probably the big takeaway here, is that it does effectively what the MV-T was doing that I showed. And then the only other one that I found of note was this IO atomic file. And basically what it did was it provided atomic updates of files in the face of competing processes. The example that they give here is Etsy password. Where do they say it? Here we go. So it says, for example, you generally don't want to be halfway in the middle of writing Etsy password and have your program terminate. So what this is doing here is effectively you are writing a temporary file, and then you are using an atomic move command to replace the old file with the new file, which you have ensured has been completely written. So you can write it outside of worrying whether or not you are modifying the actual file. And then when you have verified that you have written the new version of the file in it as a temp file, you can atomically move that swap the files basically. It's not really swap, but you can replace the old file with a new file that you know is good. And that replacement operation itself is atomic. So let's see. All right. So there's a lot of applications for this. My mind was kind of swimming when I was doing this about how to show different ways of coordinating multiple processes, and ultimately I just decided I wasn't even going to touch it because it's not something I can do in 30 minutes or an hour. And it's if I did decide to do it, I wanted to do it right. So, but there's enough flexibility here. There's enough capabilities of these easy to access atomic operations where you could get pretty fancy with how you coordinated the child processes. One example is work queuing, and I actually did this at cPanel, and I looked for the code. But at one point, we were building images for OpenStack, and I was given this shell script. That was basically iterating over a bunch of images, and there was a race condition in it. And I decided that in order to solve the race condition, I was just going to effectively create a directory, and for each image, let's say I wanted to build, or let's say generically each thing I wanted to do, each unit of work, I created a file, and then I had a bunch of worker processes that just went into that directory and just picked up a file. So it's literally just a work queue. And now the atomic, where I used the atomic operation, I think I used at the time was it was a symlink. It was ln minus s something. In any case, I didn't cover that because the blog entry said it didn't work like he thought it worked. So I just kind of moved on. But at the time, it worked for me. And all it was doing was a process. It would just iterate over the list of files that were describing what work needed to be done, and it would try to create a symlink to that file or that unit of work. Well, I was assuming that the creation of the symlink itself was atomic, and I think it is still. So I would detect if it would fail, and then if it failed, the child process would just move on to the next file, basically just trying to grab the first bit of work that it could. And the way that it was claiming the work was by generating a symlink. So that's what I mean by the work queuing pattern. You really probably don't want to do that unless you have to, but it was a fun exercise. And then I've got a couple other things. There's lots of different paradigms and ways to organize parallel processes. Trying to do something lock free. Now, what we were doing, what the examples I was showing were lock free. It wasn't there. I wasn't using locks around, the directory, creating the directory, or moving the symlinks. I was just allowing each child process to optimistically try to do those things, and then I would catch if it was an error, but that's the feedback that the program is using to handle that situation, and maybe to retry, or in the case of the MV minus T, it was actually forcing the processes to get in line and wait to be able to do their operation. So that's what's meant by lock free. There was no actual lock file, even though you can use the techniques I was showing before to create lock files. Process pipelining, that's just if you have a bunch of, it's just, I guess CPUs do it, where you've just got a bunch of threads or processes. They're kind of like, one or two steps behind one another. Yeah, that's not working. Anyway, that's a bunch of processes that are like, one step, each one is a step behind in any case. So pipelining is possible, but it just depends on how you want to use those primitives to coordinate. Let's see, synchronization points, like if you wanted to have, like you could use that MV minus T to, well, I guess you couldn't, do it out of the box, but imagine you had a bunch of child processes and you wanted them to just do their thing and then reach a certain point and then just wait until all other child processes have reached that point. And then each child process will just know, okay, everybody's here, let's go. And that's what I mean by a synchronization point. What we did with the MV minus T was more of a serialization point. That's also super useful. Let's see, efficient locking mechanism. That's kind of a repeat. So example process coordination concepts. I was talking about the sync barrier here. There's something called a critical section where, say you had something that you had a bunch of child processes running, and there's something that you wanted all the child processes to do. You didn't care what order they did them in, but they had to do it one at a time. So it's identical to what the MV-T provides you, but I'm thinking you can probably coordinate something using MV-T where you want to have that critical section. Anyway, so that's another concept, the critical section. Reduction operation, it's very similar to a critical section or an atomic update of a variable where you've got a bunch of processes they're crunching numbers or doing something, but you have a single value that you want each process to contribute to, but you need to do it in an atomic way. Then that's kind of an example of a reduction operation. A sum or an average over all processes, like an average of a number or the summation of a number. That's a min or a max value out of all processes. Those are examples of reduction operations. It's related to the atomic update of a singular value. Say you wanted to keep the max value or the min value. Now a lot of these ideas I'm getting from the OpenMP standard. So but I'm thinking that a lot of the concepts that at least are in the earlier versions of the OpenMP spec could probably be facilitated in some way. So it was enough just to list all of that out. There was no way I was going to try and figure out examples and do a poor job of it this time. So conclusion, the kernel provides efficient atomic guarantees for critical operations, and they can be leveraged to do some interesting things. They're accessible in common utilities, and this is the ultimately the main point of all of this is that they're available in Perl. Perl uses the same atomic kernel operations through the syscalls for the functions that I mentioned above and below right here. And just to summarize the shell commands, there's make dir, there's just MV, straight up MV. I did not show an example of that, but I believe that that's atomic, just moving within the same file system barrier that is. And then same applies for this MV-T, but that's for retargeting symlinks in an atomic way. And then in Perl, you got sysopen, which I thought was pretty cool. I'd never ever used sysopen before. Rename is the core move. It uses the same internally same stuff as your move command line command. Symlink does its thing, and then I didn't play with this at all, but there are other atomic operations that are available through syscall, or you could call the ones that we've talked about maybe directly. But the syscall method within Perl allows you to have generic access to syscalls based on number. And that's when I started getting into that, I was like, I was getting into how syscalls are implemented within the kernel. I had to pull out because it was getting a little too. It was interesting, but it was just getting a little too much in the weeds for me at the moment. But anyway, I thought syscall is probably a pretty interesting thing to look into at some point. Okay, this is just a bunch of links. You can check those out and probably learn a lot. And one thing I wanted to point out here was this link here is the, and I don't, this is the latest version I could find, even though GCC is like way up in version now, it's way above 4.x, but this provided a really nice summary of the atomic built-ins that GCC provides. So if you were to get into systems programming, or you know, you want to get into C, and you probably have some access. You probably have access to some really interesting and nice atomic um, methods. This compare and swap thing, this CAS is what it's called. That is a lot of times that is implemented in hardware, compare and swap, and it's done with registers, and the I don't know if it's like a standard thing. You guys may probably know a lot more about this than I do, but compare and swap is an atomic operation that is very commonly implemented in hardware, and then the software on top of it can then use that. Like, say for example, I was talking about the kernel using hardware capabilities to provide atomic guarantees. You can do you can use hardware compare and swap to do a lot of things. There's even something called a double compare and swap, which I think provides some more flexibility. But the main point there is that is a hardware based way to provide some atomicity for software. Anyway, and all this note says here is I'm not committing to doing a talk on memory based atomicity. I'm not saying I wouldn't. I have not looked into it at all. And I have a really bad habit of saying I will do that in another talk. And I don't want to do that to y'all because there's a talk from 2011 or 2013 on core that I promised that I would do. I still haven't done. So that might have to be my next one, is just to make good on that promise. Anyway, no promises on what the next talk will be. And that's all I'm saying there. Let's see what else we got here. Okay. Thank you. Any questions or comments, discussion?
Yeah, two things. One, I posted something in the chat, but it's related to what I mentioned before. Around 2005, there was this thing about the fsync command, which was common in Unix, about just a way of, after you write something, you could call that just to make sure that your stuff was actually written persistently to the disk. But apparently some hardware disks and or Mac OS itself around, they started basically lying, returning saying, yeah, it was written when it actually wasn't. And then you could have corruption concerns. And then around that time, a whole bunch of like database and other products that ran on Mac OS, they basically had to get updates to work around this because there was another command available, which was more like, yeah, it really was persisted. Apparently, the behavior change was partly maybe because Apple determined lots of things were calling fsync when they didn't need to, and there were performance issues. So it's like they basically broke that and then forced people to like do something else if they really meant it. So that link talks about it, for example.
Very
The other
cool.
The other thing I was going to say is the subject of this talk is relevant to a task that I'm currently doing, which involves basically, or a task that I'm about to start, which involves like taking a hierarchical directory of files and basically doing a batch process on them, say to produce another, the simplest case being like clone it to another, but with optional processing. And I wanted to make sure that it worked in case, say, one accidentally or intentionally called the program more than once so that they didn't interfere with each other. So your thing reminded me of that.
Cool. Yeah.
Yeah.
That's all.
That's good. That's awesome.
On your second to last slide there, Brett, that talked about critical sections.
Yes.
I actually did a lot of critical sections when I was working in Windows. It's basically analogous to, in databases, a begin transaction and either call a commit or rollback. So
Exactly.
you can do a whole bunch of things and nothing else will happen to whatever it is that you're locking, and boom, you're done. In database, it's what you lock. In the critical section, no other part of the program will run while that was running. But it does essentially the same thing.
Yes, definitely. And I tried hard not to talk about the database thing, but the analogies are very good there. So I think I'm trying to remember. So I got critical section. Where did I get that first get introduced? Probably an operating system class or something. But in any case, yeah, data, that is what you say is true. And it's a good example. So,
And related to that, there's also another concept where the concept of that you may face often in real life is that the concept of atomic actions may actually be nested. Like you may have a larger task. You may have a larger task that you want to be atomic, but within that, you could have some smaller portions which individually should be atomic. And if one of the pieces fails part way, then you may want to retry it without having to restart the entire wider thing. And at least logically, you could have transactions nested in transactions, and each one could conceive itself as being the whole thing, but it might be embedded in something bigger.
right.
Sometimes data, there are also different names for a similar concept. Like sometimes in databases, you call these save points as well, but conceptually, it's the same thing as a transaction nested inside another one. And sometimes you want to like redo just part of it or all of it,
Well, yeah, and another interesting concept, and Sun actually had come out with some hardware that did some of this, is the concept of transactional memory, and that provided hardware level atomics for doing the transaction thing, but in memory. And that was, they were trying to, I guess, make code that didn't necessarily have a lot of contention in it as optimistic as possible, because the idea was to have to roll back the memory only so often. And if you had processes that didn't normally clobber over the same pieces of memory or same variables or something like that, then you could do a lot of concurrency without any locks, and in an optimistic way. But yeah, so you mentioned the database thing, but transactional memory is also another pretty interesting related concept to that.
And actually, in one sense, with transactional memory, in a sense, you actually have a lot more options because since you're dealing with something which is ethereal anyway, you're mainly just thinking of ways of making things atomic, but that doesn't relate to persistence. And so another way you can deal with that issue, which is sort of what I do in my own projects, is like, you guys know what functional programming is, and simply by building things in a functional way, which in practice is often related to the concept of copy on write. It's just the normal concept of the language that you're always creating new values. Like the concept of editing something doesn't really exist for the most part. And so that means, and this naturally lends itself to that, because it's like you have this one thing, and then rather than editing it, you just derive a new data structure in a different part of memory. And then when you're done, then your main pointer just points to that instead. And that's sort of related to transactions, but it also means that your main logic doesn't have to worry about managing concurrency, because conceptually you're not editing anything.
Cool, man. Well, I hate to cut this short, guys, but I'm gonna have to bounce and take care of these kiddos, these child processes. But
Thank you very much. That
I
was a
enjoyed
great
it.
talk.
Yeah. Thank you guys. Y'all have a good evening. Talk to you.